Okay, this is the second time I've made this video. The first time I made it, it was 15 minutes long and posted it and was very proud of myself, and then watched it and realized that my microphone was off. So let's try this again right before class starts. So today we're going to be discussing centrifugal forces on a spinning planet. The first thing that we want to do is just imagine that we have a spinning disk. All right, we'll start with 2D and then we'll move to 3D. Spinning disk with radius r, and let's just have an object here sitting at the edge. And let's imagine that this thing is spinning. Well, we already know that because of its spinning, there will be a centrifugal force outward on this object. Could be a penny on a record player, could be a kid sitting on a merry-go-round, could be anything. A ball on a string. This centrifugal force is really not a force, it's really just Newton's first law of inertia, but it operates like a force, feels like a force, and we can calculate it like a force. We can calculate it using the same equations we do for centripetal acceleration, because in almost all circumstances the two are equal. So that means we could calculate it this way, mr omega squared, where omega is the spin rate, not v, omega is the spin rate. Or we could calculate it using mv sub t squared all over r, depending on on what variables we're given. So now we're going to take this idea and sort of expand it to three-dimensional spinning object, being we'll call it a ball, a planet, an astronomical body, whatever you want to call it. So let's just start with drawing. Hopefully that is good enough that, yay, to recognize that it was a circle. So let's have this planet. I'm just going to call it a planet just for ease. And let's have it spinning this way. Like this. And now let's go back to the equator. This will be the equatorial radius r. And now let's put a person, not drawn to scale, clearly, on the equator. So at the equator, if you imagine the spinning, it's going to look something like this. The person is going to spin around in almost in a circular motion around the equator. I might as well just draw this as a straight line. Which means that they are going to feel a centrifugal force outward. They, of course, are still going to feel a much stronger gravitation, in this case, a much stronger gravitational force inward. But you can see that as long as the planet is spinning, the net force on the person is really a combination of these two. So the net force is really the force of gravity minus the centrifugal force. The force of gravity is ma. We know that the acceleration due to Earth's gravitational pull is 9.8 meters per second, so that's not going to be hard to get. The centrifugal force, as already stated, is mr omega squared, or mv sub t squared all over r, depending on what you have. Okay, so in this case, notice how the gravitational force and the centrifugal force are parallel to each other, so that's why we're just simply, to get the net force, we're going to be subtracting these two vectors. And I picked gravitational minus centripetal because, or centrifugal, because it's, at least in the case of most planets, almost all, the gravitational force is stronger. However, let's imagine that, I'm going to switch this to red. Let's imagine that, I'm just going to zip down here. I'm going to do it again. That what if you are not at the equator? And this is where the interesting stuff happens, in my opinion. That was terrible. Hey! Bless you, the people at Mac, you're programmers. So, again, we're going to have this planet spinning. There we go. The equatorial radius was still going to still have his capital R. And let's put somebody in Woodbury. Woodbury, interestingly enough, is at almost exactly a latitude of 45 degrees. Right? So this person at Woodbury, let's have also drawn not to scale, standing right there. If you imagine as the Earth spins, this person is going to spin about this axis with a smaller distance r, I'm going to call that little r, away from the central axis of rotation. Now if you think about this, and we'll just put this theta in there, that'll be the latitude. If you think about the forces on this person now as you're sitting, probably lying in bed if you're Becca, or sitting at your desk if you're Devin or Thomas, as you spin around the world, there is a gravitational force, of course, still pulling you directly downward. But now the centrifugal force, is no longer in line. It actually spins out this way. So note that the two vectors are no longer in line. To get the net result on you as you spin around the world, or as I guess you're not spinning around the world, as the Earth spins, the net force between these two forces is a little more complicated because they're not in line. So first thing we want to do is I want to talk about the relationship between little r and big R. The relationship, if I'm just going to jump in here to the, I'll just do the geometry in red. That this triangle right here, we're trying to figure out this little r in relationship to the big R. So notice that this angle theta is the same as this angle theta. So cosine of theta is equal to r over big R. Remember, big R is the equatorial radius. The little r is your adjusted radius, depending on your latitude. So r is big R cosine of your latitude. All right, so that's going to be an important thing, because if you notice that there is an r in both those terms. All right. So now I'm going to zoom in now on the force vectors. The gravitational force, let me just jump down here, is down like this. I'm really just sliding these vectors over. The centrifugal force is much smaller. It's going to be like this. So we're going to call F sub G, F sub C. Now here is where, if we're trying to figure out the net result of these two vectors, we're going to have to add the vectors together. So I can just take... Let's try this again. I can just take this vector and move it down here, which means that we are interested in this net vector. This is still F sub C. So that's what we're interested in. Now what I'm going to do is I'm going to blow it up and down here. So this is F sub G in Woodbury. This is obviously not to scale, but F sub C. And we are interested in the net part of this triangle. If this angle, if this angle here is theta, that means that this angle right here is still theta. That is your latitude. And now there's something called the law of cosines, which is that c squared is equal to a squared plus b squared minus 2ab cosine theta. Okay, that's what the law of cosines is because it's not a right triangle. So we can use that here, that f net squared is equal to f sub g squared plus f sub c squared minus 2fgfc cosine of theta. Reminder that f sub c is mr omega squared, or mv squared over r. Sorry, not capital R. mv squared over r. And remember, r is whatever your adjusted radius is. All right, so this is going to be how we calculate the actual free fall acceleration at any given point on the Earth. we never really factored in these outward forces due to the rotating planet, because that's just, you try explaining that right away in the beginning of the school year. But as we'll calculate in a couple of problems, you'll notice that, at least on Earth, the rate at which it's spinning does not greatly affect how the rate at which objects fall. If we just think, I'm just going to switch here to green real quick. If you think about it logically, that means, though, however, that objects fall fastest at the north and south pole, and I'm talking pole, the axis of rotation, not the magnetic pole. So this is F sub c is, that's because F sub c is 0 in both these situations, because the R is 0. There's no outward force. It's exact. If you were standing on a giant record player and standing in literally the exact center of the record player, assuming your body had no width, but as it spun around and spun around, you would feel no outward force because there's no R. You're no distance away from the axis of rotation. What it also means is that objects fall the slowest at the equator, because that is when the F sub c is a maximum, because the R is a maximum. What does that mean for real life? It means that if you are in an industrialized if you're an industrialized nation and you want to have a space program, what you want to do is you want to launch your objects into outer space, into orbit, from as close to the equator as you possibly can get within your national territory, because that will maximize the centrifugal force outward, meaning less fuel, less force is required to launch objects into orbit. That's one of the several reasons why the U.S. launches from Cape Canaveral in southern Florida, or we launch from Texas, which is south. There are a couple other reasons why we do that, but that's one of the reasons. And in fact, Russia has an enormous amount of territory, and they have their space station, their space center located in the southern part of their territory. So that's just an interesting bit of physics there. So that what you can also imagine too. No, I'm sorry. What you can also imagine too is that if an astronomical body was spinning fast enough, it is entirely possible that the outward force, the centrifugal force, is greater than the gravitational force. What it means is that no object could ever land on the planet unless there's some continual, force downward pushing them towards the surface. But you can't land in the sense that you land and become motionless, because the second you're on the surface, you're being jetted out again. There are actual astronomical bodies like this, quasars, pulsars, things like that, that spin so fast that you'll never be able to land on them. What it also imagines is what would happen if the Earth, Superman started flying around the Earth and accelerating the Earth's rotation. At some point, when you dropped an object, it would just float there, because at that point, the centrifugal force outward will be equal to gravity. And if Superman were to spin the planet even faster, when you, quote, drop something, it would actually fall upward, because the outward force is greater than gravity. So anyways, it's just an interesting bit of physics here. So that is how we calculate the centrifugal force on a spinning planet, and importantly, how we actually get the true free fall acceleration on a planet, because for the true free fall, we do have to incorporate the physics of the spinning, the centrifugal forces.